Okay, today we're going to continue on our lesson on the natural exponential, but this time we're going to do antiderivatives or integration. Okay, so we saw last class that if f of x equals e to the x, then the derivative of f of x is e. So that means that when we go backwards from e to the x, we end up with e to the x, but plus c. There could have been a constant that disappeared during the differentiation process. Okay, the only exception to that is when we have a power that's not just x. So remember from the derivatives that this is the inside part of the exponential function. E is just a number, so the input is where the x is substituted into the 5x. Okay, so we do have the chain rule to apply when we take the derivatives. And the way that we undo the chain rule going backwards is use substitution. Okay, so we're going to do a couple of these with use substitution. And then we're going to talk about the one process in which we can use a shortcut. And then most of them are going to be u sub or either what I call simple e. So for example, if I were to do number 1, there is nothing around the e, so e is our outside function, which makes the inside function 5x. The derivative of u is 5 times the derivative of x. So that makes 1/5 du equal to dx. Now I'm ready for my u substitution. So the dx part is replaced by 1/5 du, which case I'm going to take the 1/5 and put that out in the front because we can factor out a constant. And e to the 5x is replaced by e to the u. So when I antiderive, I get 1/5 e to the u plus c, which is 1/5 e to the 5x plus c. Similarly, on this one, e is not inside for number 3. We're going to do number 3 next. E is not inside of any other function, which makes the only inside part x squared. So the derivative of u is 2x dx. That means when I'm substituting out, I actually have a perfect substitution. I have exactly du, and then I also have e to the u. So that goes backwards to become e to the u plus c, which is e to the x squared plus c. Okay, let's do one more where we have to do u substitution. Okay, so if I were to look at number 4, since e is not inside of anything else, the inside part is 1 over x, or x to the negative 1. That makes du negative x to the negative 2 dx, or negative 1 over x squared dx. If I compare to the fraction that I already have, I'm going to pull out the 1/2. I have e to the 1 over x squared dx. So except for the minus sign, I have a version of du. So 1 over x squared dx is going to be negative du. I already had a 1/2, and now what's remaining is e to the u. So the negative 1/2 stays on the outside. I antiderive and get e to the u plus c, which makes this negative 1/2 e to the, replace the u with 1 over x, plus c. Now, I said there was going to be a bit of a shortcut, and that's only going to be true when we have functions or equations that are what I like to call simple x. If I have, or simple e. Simple e is when I have e raised to a power without having any other variables with the e. So for example, on number 3, I have a 2x with the e. Can't do that one. That's not simple. Here I have e to the u, but something more complicated. And for number 5, I have e to a power, but another function. However, Number 2 and number 1 are both perfect examples of what I would call simple e. So I could factor out the 4 and have e by himself. If it's possible to get e by himself, then I like to call that simple e. If I have a simple version of e, then I don't actually have to use substitute. I would hold the 4, and the antiderivative of e to the 1 minus x stays with e. But think about how you would have done the derivative. If I had done the derivative of e to the 1 minus x dx, I would have kept the e and then multiplied by the derivative of the power, so negative 1. So when I go backwards, I'm going to do the same idea, but instead of multiplying by negative 1, I'm going to divide. And then plus c. So negative 4 e to the 1 minus x plus c would be the correct answer. If we had used substituted, we would have gotten the same thing. So let's go back and look at number 1. If we use our shortcut method, this is a simple e by himself, then the antiderivative is keep the e, and instead of multiplying by 5, we divide by 5, plus c. And notice we got the same answer. Now what I want to caution you about, most common mistake that I see students make, e is not the same as x to a power. If I have 2 over x, 2 to the x, that is not the same as x squared. So it's the same idea. So you can't use the power rule to go backwards. Okay, so let's look at number 5 and number 6 and decide. Okay, with number 5, this is definitely much more complicated. I have a function outside, so I'm going to do my u substitution, and u is going to be the sine x. So du is cosine x dx, and I have a perfect substitution. Cosine x dx is exactly du, and then I have e to the u. So the antiderivative of e to the u is e to the u plus c. So it's e to the sine x plus c. Now number 6, I want to have a little sidebar. If I had x to the 5th divided by x squared, I would get x cubed because I subtracted my exponents. I'm going to do the same process. I'm going to rewrite this as e to the 4x over e to the x plus 2e to the x over e to the x plus 1 over e to the x dx. So I'm going to use the same process from here for this part. I'm going to subtract my exponents. So 4x minus x is 3x. The e to the x's for the next part cancel out. And then I have 1 over e, which is e to the negative x dx. Now, in comparing whether I need to do a u sub or not, if you look at each of these separately, I would have to do 2 separate u substitutions for each of these e's, which we would like to try to avoid, which is why I want you to know the shortcut. This is plain e, not multiplied by anything. So complicated, have to u sub. Plain e, no u sub. So the derivative would be multiplying by 3. So the antiderivative is dividing by 3. The antiderivative of 2 is 2x. And antideriving e to the negative x is, instead of multiplying by negative 1, I'm going to divide by negative 1. So my final result could be written as 1/3 e to the 3x plus 2x minus 1 over e plus c. Okay, 7 is another perfect example of simple e. So when I antiderive, there's no u sub. So it's e to the negative x divided by negative 1. And since there's no u sub, there's no reason to change out my limits. I would, before I substitute and simplify, I would pull out the negative 1, write this as 1 over e to the x before I substitute in. We don't want to make any substitution errors because of the fact that we have a negative power, so we're going to fix that. So I'm going to leave the negative 1 outside. This is 1 over e to the 1 minus 1 over e to the 0. So that's negative 1 over e minus e to the 0 is actually 1, so this is just 1. Now, if this were a free response, this is the point where you could stop. However, if you had a multiple choice, they would distribute, and you would have positive 1 and negative 1 over e instead. Okay. Number 8 definitely requires a u substitution, but the outside part is not e. The outside part this time is sine. So u is equal to e to the x. So du is equal to e to the x dx. So I want to substitute out my du first. So my e to the x dx is going to be du. That leaves behind the sine of u. Now my limits. I have to do u values instead of x values. And so u is e to the natural log of pi, which is just going to be pi. And u is e to the 0, which is going to be 1. So, like Taylor Swift, we are never, ever, ever getting back together with our x because we have limits. So we're going to anti-derive sine and get negative cosine of u from 1 to pi. I like to keep that negative factored out, so I'm going to close off that bracket. So I have negative cosine of pi minus cosine of 1. That's negative 1 minus cosine of 1, which we cannot do, which means we simply leave it written that way. So if this were a free response question, you could stop there. On a multiple choice, however, they would distribute the negative, and that would be positive 1 and positive cosine of 1 radian. And 1 radian is just somewhere slightly smaller than pi over 3, but we just don't know the value. Okay, so for the next one, our u is going to be cosine of x. So du is negative sine of x dx. So negative du is what we'll substitute in for sine of x dx. So this part becomes negative du, and then we still have e to the u. So the antiderivative is negative e to the u plus c, or negative e to the cosine of x plus c. Okay, number 10 tends to throw students off sometimes because of the way that it's written, but notice how e is not inside of something else. That means that u has to be tangent x, which means du is secant squared x dx. That is a good hint that I probably want to rewrite that cosine. So think about this as e to the tangent x, and then 1 over cosine squared x dx. So I really want to rewrite this part. I have e to the tangent x, and cosine on bottom is really secant. So then I have a perfect e to the u du, which antiderives as e to the u plus c, which is e to the tangent of x plus c. For number 11, we're going to want to FOIL this out. We cannot let the inside part be u, because we don't have a du on the outside. There's no derivative of e on the outside. So I would rewrite this, however, as e to the x plus 1 over e to the x times e to the x plus 1 over e to the x. So we're less likely to make a mistake. That means the first term is e to the x times e to the x, which is e squared to the x. So we're not squaring the x. We're squaring the e. It's e times e raised to the x. Plus, when I do the inside part and the outer part, notice that I'm getting e to the x times 1 over e to the x. That's really going to be 1. And then the outside part's giving me the same thing, 1. And then the last part's giving me 1 over e times 1 over e, which is 1 over e squared to the x. And then we have dx. So I'm going to rewrite that a little bit more. So it's e to the 2x plus 2 plus e to the negative 2x dx. So now we have everything in the format of simple e. Since we have simple e, the antiderivative of e to the 2x is e to the 2x divided by 2 plus 2x plus e to the negative 2x divided by negative 2 plus c. So on the derivative we multiply, on the antiderivative we divide for simple x. Okay, for the next one, e is inside of something else, which means the outside function is not e. The outside function is the square root. So our u is going to be 4 minus e to the x. So du is negative, and then the derivative of e to the x is e to the x dx. So negative du is going to be substituted for e to the x dx. So e to the x dx is negative du, and then on the inside we have the square root of u. So we have negative. Now remember, this is really u to the 1/2, so it's going to be u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, plus c. So negative 2/3 u, which is 4 minus e to the x, to the 3/2 plus c. We did not have limits, so we had to get back the x values. 13 is going to be simplified very much like number 6. So it's e to the 2x over e to the x plus 2 e to the negative x over e to the x plus 1 over e to the x dx. So if I want to get this into simple x format, this would rewrite e to the 2x over e to the x is just e to the 1x remaining plus 2. Now I have e to the negative x and another e to the negative x on the bottom, so I actually have negative 2x for e, and the last term is just e to the negative x dx. So if I move each of these terms up, this would be a negative x, which cancels one of these. This is going to be a negative x, which makes 2 negative x's up there, and then 1 negative x. So using simple e, this is just e to the x divided by 1, plus 2e to the negative 2x divided by negative 2, plus e to the negative x divided by negative 1 plus c. So you would see this is e to the x minus 1 over e to the 2x minus 1 over e to the x plus c. Okay, number 14 is not simple e. It has to be u subbed because what we have multiplied by e, so e is not alone. So that means that my u is the square root of x, or x to the 1/2. So du is 1/2 x to the negative 1/2 dx. That means we have a perfect substitution. I have 1 over 2 root x dx. So I have a perfect du. That means when we rewrite, we have e to the u, we have du, and since it's du, we have to get u shoes, or u limits. So u is the square root of x, so the square root of 9 gives me 3. U is the square root of 1 would give me 1. And since we have limits, we never, ever, ever get back together with our x. So e to the u is the antiderivative from 1 to 3. So I'm going to get e3 minus e to the 1, which you might see written as e times e squared minus 1. Okay, number 4 is simple e. So my u is just negative x, but I don't have to do that. So I'm going to go backwards. The antiderivative of e to the negative x is e to the negative x divided by negative 1 from 0 to 4. Since we did not have to do a u substitution, we don't have to change out our limits. So I'm going to rewrite this though as negative 1 and 1 over e to the x before I substitute in. So we have negative 1 over e to the 4th minus 1 over e to the 0, which on a free response can be negative 1 over e to the 4th minus 1, because we have to show that we know what e to the 0 is. On a multiple choice, they would distribute the negative and make positive 1 and negative 1 over e to the 4th. Okay, the next one, e is not alone, so we have to u sub. So our u is going to be, I'm going to rewrite this as negative 1/2 x squared. So it doesn't look like it's a quotient rule because it really doesn't have to be a quotient. So du is going to be negative 1x dx. So negative du equals x dx. So we're going to substitute out x dx is negative du. That leaves us with e to the u. And since we are in terms of u, we have to change out our shoes, are our limits. So u is negative 1/2 of x squared. So in this case, that's going to be negative 1. And u is equal to negative 1/2 of 0, so 0. But notice that these limits are in the wrong order, so we're going to flip. So that makes us positive from negative 1 to 0, e to the u du. So we antiderive, we keep e to the u from negative 1 to 0. We never, ever, ever get back together with our x. Like Taylor Swift, we have limits. So it's e to the 0 minus e to the negative 1, which is 1 minus 1 over e. Okay, for these questions, they're written out and they tend to confuse students a little bit, but the area bounded by a graph and y equals 0 is really the x-axis. Well, that's what we've been doing the whole time. We're finding the area, really just means the integral. So we're going to do the integral of e to the 4x dx from x is 0 to x is 1. Left off my x. Okay, so now this is simple e. So it's e to the 4x divided by 4 from 0 to 1. So I'm going to keep the 1/4 out and do e to the 4 times 1 minus e to the 0. So this will be 1/4 e to the 4 minus 1. Okay, for the next one, we again have the x-axis. Oh, can't spell. It's a good thing I teach math. X-axis and a curve, which means we're doing the regular integral, and they're telling us from 0 to 4. So from 0 to 4, we have e to the negative x dx. This is simple e, so we keep e to the negative x, and instead of multiplying by negative 1, we divide from 0 to 4. I'm going to rewrite as negative 1 on the outside, 1 over e to the x before I substitute in. So that's negative 1 on the outside, 1 over e to the 4th minus 1 over e to the 0. So that makes this negative 1 over e to the 4th minus 1, or 1 minus 1 over e to the 4th. Okay, the next one's a little bit trickier because they didn't give us both of the x's. They're still telling us curve and x-axis, so it's still just a regular integral. However, we have to know that we're starting at x equals 0 and where to end for the next spot. Okay, so if we're starting at x equals 0, we need this to be bounded. Okay, we have to remember that e to the x is never going to be negative or 0. That means the only thing that can make this 0 is if sine of e to the x equals 0. That means that whatever is inside the angle e to the x has to equal something that would make sine 0. So that would be 0, pi, 2 pi, etc. So we're going to choose pi so that it's the very first one so we can get that area. So that means that we have e to the x equals pi, which means that we have to natural log both sides. And so x equals the natural log of pi. Okay. Now, on this one, e is inside of something else, so I have to u sub, which means that du is e to the x dx, since u is e to the x. That means I have a perfect u sub of sine u du. And if I substitute in, I'm going to get my u values are e to the natural log of pi, so just pi, and e to the 0, so 1. So we get the antiderivative as negative cosine of u from 1 to pi, which is negative cosine, in parentheses, pi minus cosine of 1, which is positive 1 plus, because cosine pi is negative 1, positive 1 plus cosine 1. Okay. For the last one, let's just set this one up. Since we've already done this antiderivative previously, over here, we're just going to rewrite this. So we are talking about from x is 0 to x is root 2, the x-axis, y equals 0, and the curve. So it's a regular integral from 0 to root 2 for x e to the negative x squared over 2 dx. Now make sure you are including your dx. Oh, that looks funny. Let me try one more time. Because it has to be area. And so remember, area is y times x. So the dx is just as important on this notation. Okay. For the next part, they're giving us the acceleration function, and the first question asks about velocity. So we have to remember that the way this works is it's position, velocity, acceleration. So if we're going down, we would be taking a derivative. Going up, we would take an integral. This is not like sine and cosine, so we can't go around in a circle on this. Okay, that means we want an expression for v of t. So v of t is the antiderivative of the acceleration function with respect to time. Remember the dt is important. So I'm going to hold the 10, and this is simple e. So e to the 2t divided by 2 plus c, or 5e to the 2t plus c. We're then going to use the initial condition to solve for c. So v of 0 equals 5 means 5e to the 0 plus c has to equal 5. And that means that c equals 0. So our velocity expression, or velocity equation, is 5e to the 2t only. Okay. Now the next part says, during the time the velocity increases from 5 to 15. The most common mistake is that students skim through this and it says during the time, and they assume the time is 5 to 15. But it's not the time, its velocity is from 5 to 15. So we know that at time 0, the velocity is 5. The question is, what time would the velocity be 15? So I'm going to set the velocity function I found above equal to 15, which means e to the 2t has to equal 3. So if I natural log both sides to get rid of e, 2t equals the natural log of 3. And now I have a lot of students write like this, so don't write this down. Don't do it. I have tons of students who do this, and somehow by the end of their problem, when they're doing the integral, it starts to look like this, and by the end they're doing the natural log of 3/2, which is wrong. So don't do it that way. Okay, definitely not the same thing. We saw with our log rules last class that technically this is 1/2 natural log of 3. This would be the square root of 3, not half of 3. So if we were to put that power up, it would be completely different. But leave it as half natural log of 3. So we're doing the integral from the time 0, where velocity was 5, until time half natural log 3, where the velocity is 15. And we're anti-deriving velocity. Technically, we're doing total distance traveled, so it's the absolute value of velocity. Now, I'm going to write down the appropriate integral with the absolute value because it's total distance, but because e is always positive, I can ignore the absolute value. It really does nothing to the equation, but only because velocity is always positive. So I'm going to hold the 5, anti-derive simple e again, as e to the 2t over 2, from 0 to half natural log 3. That means that I have 5/2 parentheses e to the 2 times t, which is half natural log 3, minus e to the 2 times 0. So that's another reason I wanted this half out front. The 2 and the half just cancel. But that now means that I have e to the natural log of 3, which means the e and natural log will cancel, but only because the half was got out of the way in the first place.